Alright, well, I'm still at the airport. Let's look at separation of variables still. Here's an example. So, example. Suppose we have something like, and this time I'm going to write it as dy dx equals, let's say we had something like x plus y, or x times y, not plus, plus y, something like that. And now we need to separate these variables, but again, the whole idea is that you want to get these, on the left side, a function of y times dy dx. And so here, if I just subtract y from both sides, that's a problem, because one, I've left a y over here on the right side if I simply subtract the y on the right over there. And so that's just not going to do it. I have to get a multiplication on the right side to begin with. So here, dy dx, if I write that as y times x plus 1, then that's a multiplication, and I can divide both sides by y, and I get the 1 over y thing again. You'll often, if you can separate variables, you'll often have something like 1 over y, or some other sort of fraction when you get this, because you end up dividing both sides by whatever your function of y is on the right. And so we have our 1 over y dy dx equals x plus 1. So now, again, remember the way this works from here is I integrate both sides, 1 over y dy dx with respect to x, and this side, x plus 1 dx. Now, if you look there, it looks like dy dx ought to be dy. And yes, it is. And that's part of the reason that the Leibniz notation is so nice, is when I take this thing, dy dx, which is not a fraction, it's a function. It just has a very complicated looking name, but it's just a function. And dy dx, but when I take that times dx, part of the reason we like the Leibniz notation is the answer, dy, looks like we had just done some sort of fraction thing and canceled things out. But that's not really quite what's going on. So here we have our 1 over y dy equals our x plus 1 dx. Now, back at this step, way back here, again, what you'll often see people do is, without using any integration signs, they'll simply start from this top thing here, divide both sides by y, but then write it as dy over y, okay, equals x plus 1 dx. And so what it looks like is they simply multiply both sides by dx. Well, actually, that's true. If you do multiply both sides by dx, then you can kind of forget that you don't have the integral signs yet, but you still have on the left-hand side a dy dx times dx, and that is still dy, even if you're not taking the integral. And so you'll often see people do something like this, especially if they started with this fractional notation or Leibniz notation of dy dx. But at any rate, we get to this integration down here. We have to do that integral, and once again we get natural log of the absolute value of y is equal to, in this case, x squared plus x squared over 2, plus x plus c, an arbitrary constant, and so now we have the same situation we had before. The absolute value of y sides, I get e to the x squared over 2 plus x plus c. Now, notice that this could be written as e to the c times e to the x squared over 2 plus x, and that's often done. And then, since we don't know what c is anyway, you know, it's just an arbitrary constant, well, e to the c is also just an arbitrary constant, and so we'll have that the absolute value of y is equal to some other c. Now, what you might want to do, it's often not done in the literature, but what you might want to do is, well, okay, this c that I'm writing here is not the same as the c that I had there. It's actually the exponentiation of that c. So you might want to put like a c1. I'm not going to grade you down if you don't, unless you get things wrong. Another announcement going there. So here's e to the x squared over 2 plus x, like that. And now I can get rid of the absolute values, y equals, and again, it's either plus or minus c1 and e to the x squared over 2 plus x. But now, remember what I said is that we don't really know if it's the plus or minus until we get some initial condition. However, we don't know what c1 is. C1, you know, at this point, with that plus and minus, c1 could, you know, we could make it plus c1 or we could make it minus c1. Now, I know back here that c1 has to be a positive number, but if I turn it into a c2, e to the x squared over 2 plus x, now, all of a sudden, I can drop that plus or minus thing and just wait for the initial value. So it's kind of weird in that back here, this first c, when I add it, c is an element of the real numbers. Now, when I go to the c1 here, though, c1 is greater than or equal to 0. And then, when I go here to c2, that's actually any element of the real numbers again. And so you see, when we mess with that arbitrary constant, it can be that you could sort of go right through this and just kind of go, oh, well, that's e to the c, but e to the c is just some other c, but you don't put a subscript on it, you just say it's some other c, and then, oh, but plus or minus that c is just some other c. Well, so what could happen is you could get down here and write as your answer y equals c e to the x squared over 2 plus x. You could have an initial condition that said something about you know, y being negative for your initial condition, and so you would end up with a negative value for this c down here. And you might, you know, if you weren't paying attention, you might never realize you actually had a moment in there where you couldn't have had a negative value for that arbitrary constant, okay? But that was back here at this step. But it's just one of those things. Sometimes you can get lucky in math and make sort of two errors or an omission and actually end up with a correct solution in the sense of the function here. However, you know, one could definitely say that if you weren't explicit in going from this step and say you didn't have a C1 on there, this step up here with the absolute value to this next step here where we drop the absolute value, but it, other than the subscript, it looks exactly the same. You know, one could argue that your solution is wrong. It has a flaw because you needed to justify how you got from here down to there. And you needed that plus minus in there to do it. You know, those are just some small things that you can, again, many, you know, if you do a lot of these differential equations, you know, you may get kind of lazy and not worry about such a thing, you know, because solutions work out just fine and so forth. But I would like to point out that, you know, the rigor part of it is that, you know, these values, these arbitrary constants, in some sense, even though we don't know their value, they are different constants. We don't know what they are, and so in that way, we just kind of bring them along.
Requesting a wheelchair at the American Airlines ticket counter, please. One wheelchair, American Airlines ticket counter. Thank you.
Anybody got a wheelchair? But at any rate, I think we're done with this example. Here's our solution for our general solution. That's the fashion police coming to get me. There's our general solution. Again, if we had an initial condition, we could stick that in, and maybe we'll have time for an example like that.